Okay, and what I want to do today actually is kind of to review review the thing that we have done, and also I'm gonna change things a bit that I like. Basically, in the last 4 lectures, we talk about decremental shortest path, right, and push the level. And they are kind of based on core data structure, both of them, which is to maintain TightEdge data structure, right? And there is another one called Approx TightEdge Data Structure, and I actually update this one in the lecture note. So these 4 lectures, all these 4 lecture notes are updated, and you can have a look. And I'm just gonna kind of go through them quickly today. How I update it and it improves things a bit. Yeah. Okay. So the part that is updated is about Approx TightEdge data structure only. Okay. Approx TightEdge. This part is updated. Okay. And how is this updated? The key point is that we used to talk about like 1 plus or minus epsilon stretch. This notion, right? Which means like it's kind of stretched up to some multiplicative factor. Okay. Now I will change this thing to additive error notion, meaning that, and we'll see, like I'm gonna update this from multiplicative to additive. That's the key that it changed, and I think it makes things a bit better, and at least it improves some bounds in what we have seen. So, yeah. Okay. So, okay, here is the notion that we looked at before, right? We have H, and H is relaxed if like level of U is like not too much higher than B, like U is not more than B by this much, otherwise it's stretched. Okay, so this is just the old thing. Okay, and now I'll just gonna talk about this. Okay. Here is I will say that an H is alpha relaxed. Okay. If the following is true, in class I used to just write alpha relaxed if this is less than alpha times the weight, but now we're gonna change it to alpha plus alpha instead of times alpha. Okay, just a simple change. Okay, and again, I just for intuition, when alpha is less than 0, it means that if it's alpha relaxed, when let's say alpha is -1, it means like it's over relaxed by a bit, right? And if it's more than 0, then this is the case when like the edge can be overstretched by a bit, but not by more than alpha. And we can talk about beta stretch. And here, instead of beta, like times the weight, it's just plus beta. The same thing, like if alpha is beta is more than 0, it means that E is overstretched by beta. And if beta is less than 0, it means that E can be relaxed a bit, but not by more than beta. Okay. So just for the one who come a bit, I basically update the notion from multiplicative stretch or relax to additive one, and it will improve the bound a bit. Yeah. So this is just about review of old stuff, but improve things upon like on the way. Yeah. Okay. Okay. So now we can talk about edge slack function. Okay, and we can say like for any edge set, it is, let's call this delta. Yeah, is the delta slack, delta relax. If for every edge, E is delta E relax. For every like yeah, if for each edge in F, E is delta E relax. Okay. Okay. And then we can show this thing. Like this is just the same lemma that we have seen, but just changed to additive notion, which is now if every edge are delta relax, then for every pair UV, the stretch between U and V is at most the distance, but this is distance in terms of W plus delta. Okay. Which makes sense, right? Like you can relax, like it's relaxed, but like it can be a bit more overstretched by delta. So you can relax, like it's relaxed up to plus delta. Yeah. And if there is the minus delta stretch path, what does it mean? It means that it's basically almost tight. Every edge on this path is almost tight, but it can be relaxed a bit by delta. Okay. Then it means that like this thing is still quite stretched, but like this thing is like stretched like by more than distance, but actually the distance is distance on W minus delta. Okay. So if this is true, then like it means that this thing is sandwiched between the two here. Okay. And the proof is just the same thing. Okay. The proof is just like if there is a look at any path here, if all edges are relaxed, then if you look at how much the U and V are stretched, you sum them over all paths. Sum this difference of level over all paths, and then because this edge is relaxed, then this term is at most this term plus this additive thing. But this is what? This is just like the weight of W plus delta summing over all paths. So, okay. And because this thing holds for, so like this is at most this one, and it's true for the shortest path. In like this whole even for the W plus delta shortest path, which I mean like the shortest path with respect to this weight. So it means that this is at most this, which is the distance in terms of W plus delta. And if there is a path that is minus delta stretch, then what you get is kind of the same thing here, except that this is stretched, so you get this at least. And it's minus delta stretch, so you get this term minus delta here. So it means that this thing is at least W minus delta of P, but W minus delta of P is at least the distance in terms of W minus delta. Okay. So it means that like, you know, like everything here is always bounded by here, and if there is a minus delta stretch path, then the stretch between you and how far away U and V is sandwiched between this one and this one. Does this make sense? It's kind of the same thing, just changed to additive stuff. Okay. And So I also changed the notation, like this one less than alpha, it means alpha relaxed. More than beta, it means like the set of beta stretched edge. Okay, and if this is 0, if alpha is 0, it just means relaxed edge. Yeah. Okay. All right. And how does this kind of help? Okay, good. So now the notion of this approximate TightEdge data structure, I used to use epsilon here. Now I put delta, where delta again is a kind of, a function, right? A slack function. Okay. And the invariant now would be that every edge is delta relaxed. And if any edge is delta stretched, it should be active. And if it's active, then it's minus delta stretch. Okay. So if it's really stretched by more than delta, it should be active. And if it's active, it should be quite stretched, but you allow this slack. Yeah.
But under the delta, each edge has its own threshold.
Yeah, each edge has its own delta. Yeah. We just use this as the notation. Yeah.
Got it.
Okay. All right. Okay. And now, like, the idea is then that, like, how do you maintain approx TightEdge? Well, like, first you initialize so that, like, anything that satisfies the invariant, for example, set everything to be 0. Yeah. But how do you maintain the TightEdge set, right? I just make it more clear here that when the level has increased by at least delta, then you probe it. Okay. So like you basically, like delta here is like the frequency of how you probe the edge, basically, right? It used to be epsilon times the weight, but now it's just delta. Okay. And what do I mean by probe? I mean, like, just check if it's stretched or not. If it's stretched, then mark it. If it's not stretched, then unmark it. It's just that we don't check this every time. We just check it every time that the level have increased by some amount, which is delta. And with this, then we basically can maintain the TightEdge one, like, and like, I will not go over this, but I hope you kind of see it intuitively now that, like, this should be true. Okay. It's just every edge have its own frequency, and you just check whether it should be stretched or not. Okay. Okay. Whether it should be active or not with like a delta frequency. So you get this kind of thing. And the running time is basically you pay per edge, you pay h over delta. Okay. Okay. So far it's just the same thing, right? Is any question about this? Right. Okay. So what does this buy us? Okay. This kind of help a bit because in class I present the one which is an approximate decremental shortest path algorithm on DAX, which is where this thing is like epsilon square. But we can get epsilon actually. Okay. So basically the reason that we pay epsilon square is kind of just because of It's just some clumsiness of how we use the notation, and yeah. But here it's going to be clearer that we can improve this a bit. So I use this version. Okay. So good. Let's recall the algorithm for decremental shortest path on DAX, right? So let's see. Yeah. The problem is like you have a DAG with topological order tau, a sink, and some parameter d and epsilon, and the graph undergo edge deletion. And what you want to maintain is like this approximate ball of radius around d. If anything has like any vertex v that has distance less than d, we should be in your ball, and if it's in the ball, then it should have distance close to d. Okay. That's the problem. Anyone recall the algorithm? What do we do to maintain this?
You do something like add some edge weights based on the topological order.
Yes.
To basically like relax somehow like multiplicatively less edges like based on the new distance. So like you are long edges will.
Actually, good. We do something related to topological order. Yeah. But let me even like ask you a more trivial one. Like suppose that even just to can you recall the algorithm for maintaining distance exactly? Actually, what do we do there? Like the one that spend maybe mn time, or like the slow one. What do we do?
Was this the one where we just put like the forward just one, backward just nothing, and just plugged it in, or is that something?
No, that's for MacFlow.
That's where I saw it.
This is like just for decremental shortest path. So you recall that like
Didn't we just like run TightEdge and delete when they got tight?
Good. Yeah. So you said just run TightEdge Data Structure. So that's true. If we maintain TightEdge Data Structure, any edge that is tight will be part of shortest path. So that's good, right? That seems like a good thing to do. But if I just start with like everything has level 0, then no edge is tight. So the TightEdge data structure is just maintaining the current set of tight edge. It doesn't reveal me the shortest path at all. What should I do to?
And then we, if it's like not at the end of the tag, we just start like relabeling, right?
Yeah, exactly. Like so. Like it's like in the beginning, maybe everyone is at level. Every node here is at level 0, right? Nothing is tight, like the whole graph is at the one point. But now we know like if any edge is tight, it will show us the shortest path. So what we do is just we try to play gravity. We just try to pull things until something is tight, right? So just check if the X is a node V or U, such that the tight edge incident to U that go out of U is empty. If it's empty, what should we do? Just relabel it. Like it doesn't. U is not tied to anything. So it means that we can pull it so that like it increase, U is now increased. Maybe now it's at level 1. And just keep pulling everyone until it's tight. Just play gravity, really. Like decremental shortest path is to play gravity. Okay. And this algorithm will basically be the algorithm for the exact shortest path, like exact algorithm, right? So you keep pulling things until like maybe you keep pulling, maybe U is here, and then maybe V is here. Then you pull V is here, and now this edge is not tight, so now you pull U again. You see, just keep pulling. And if maybe I delete some, like suppose that everything is tight now. Now like you allow the user to delete some edge. Oh, right? Like until like everything is tight. Like until for every node U, there's something that is tight out of U. How does it look like? It will look like kind of like this, right? Maybe like so like every edge has some tight edge out of it. So this is just going to be your shortest path tree. Right? And okay, there's maybe some edge is not tight like this, but everyone is tight. Everyone has some edge tight going out of it. And maybe if I delete this thing, now I just check if like this guy have no tight edge out of it, so I relabel. So I just increase this, and it's not basically here. So this is now like a new shortest path for this guy. Okay. Okay, so that's the algorithm for decremental shortest path. But it can be slow. It can have like its running time is something like m times h, if h is your kind of threshold of. Yeah. But in general, like the length of the shortest path here can be as big as NW. So the running time here is like is slow, and it's slow. And we do something else. We show how to get something like this thing, right? This one. Anyone recall what's the idea? Yeah.
Is that where we kind of scale up the weights so to like the nearest multiple, I think, of d epsilon over something, and then we create the TightEdge data structure on the updated weights. Or...
Yeah, right. Here is like what we do is like we basically say that maybe instead of like right now everything here is a multiple of like this is 0, this is 1, this is 2. 3, 4, and so on. We just kind of be more coarse-grained and say that like let's put kind of every node kind of jump the level by more like larger multiple, and this multiple is gonna be something like epsilon d over n. So it's kind of more coarse-grained. And you can check that it gives you this. All right. Okay, that's the MN algorithm for weighted graph, and it gives. But because like we kind of skip things, like it's a bit coarse-grained, so you need to pay some approximation, right? Okay. Anyway, this is just to recall stuff. But now we're gonna see the algorithm for DAX, which is like faster, it's n square. Right? And good. Okay, so the algorithm is basically similar. And what we're gonna do here is like we maintain Approx TightEdge Data Structure where the slack. Now I have a slack function, and the slack function is just this. It's like this multiple here, like the same multiple here, but like if the edge is far in topological order, then the slack is bigger. Okay. Okay. And I just use the same weight from the graph here. Okay. Like so in class, like previously, I just kind of changed the weight a bit, right? But here, I just use the same weight, but I just say that each edge with this weight has some slack, and the slack is just this one. Okay. It's just, it looks a bit cleaner. Okay. And when we delete, we delete. And what we do is like we try to play gravity like before. As long as there is some node that's not tight with it's not tight with anyone, just pull it. And you pull it by this multiple. Similar to the idea here that everything is a multiple of this. Okay. So that's the algorithm. Okay. So does it make sense? Like we just still like play the gravity, pull everything, try to be faster using this multiple. Like everything just jump by this multiple. And also another idea is just that every edge here just need to be approximately tight. The edge in the E prime set just need to be approximately tight. By how much? You have the additive slack of delta for each edge, delta E for each edge E. And the slack is different for every edge. It's this one. Okay. And you can see that, yeah, this is just like, for every node that whose level is less than h, we get that the level here is kind of close. It's basically the shortest path, like the distance to t, but we have some slack, some additive slack here. And why is that? Well, like I will not go over it, like because it's kind of the same proof, just change multiplicative slack to additive slack. Okay. Okay. And one thing to note is this. With this additive slack, it's basically the same as like the distance after minus or subtract or adding this slack is basically the same as the distance in the real graph, but with this factor. And this is where we use that the graph is a DAG. In a DAG, with this slack, you just need to pay this much. So why is that? This is because, let me just show this first one, right? If you look at any path from V to T, right? Such that this is like a shortest path. This is a path that, this is the shortest path with respect to W minus delta. So the length of this path is just the distance. So we know that this thing, just by definition, is this. And this one, this is some path in W. So this is at least the distance in W. But what is delta of P? Delta of P is just the sum over all edge in P. And this is just sum over edge in P delta E. Delta E. But delta E is just this thing, right? This thing times this thing. But this sum in the DAG, this sum is at most n. Because it's a path that go forward in DAG, but it go forward in DAG. So the topological order can increase by at most n. This is n. So this is at most. This is just at least, yeah, at least. This one. Okay. And okay. And I hope you can and with this we can say that the ball that we maintain is basically correct. Because if it's in the ball, then we know that the level we said that the ball is the guy that the level is small, by this small. This is how we define the ball here. Okay. So if the level is small, then we know that the level what is this? Okay. But we know that the level is at least this one, which is at least this one. So it means that right? Because the level is less than h here. So if the level is less than h, V is kind of stretched. So V is at least this one. But this is basically the same with this weight is the same as W here with this lag. So we can conclude that the weight of W is at most this. And similar here. Yeah. Yeah. So the proof kind of it seems to me that everything is a bit cleaner. Yeah. And the running time is just that it's just a time to maintain approx TightEdge data structure, which is this term. This is a term for probing, right? For probe. And this term is for relabel. You have a n node. Each node will be relabeled at most h over this many times, because every node kind of increased by this multiple. Okay. And now you can see that and this is the number of edge updates. And I just calculate. And I kind of used to pay twice, 2 factor of epsilon here, but now it's just 1 epsilon. So it's a bit better. Okay. Good. Okay. Any questions? And this is just to maintain one threshold. And if you want to remove the threshold and obtain the approximation, you still need to pay. Just run data structure for every scale d, for d equals 1 plus epsilon to the I, and this will create this many data structure. So the total running time is this one that we get multiplied by this one. Okay, so that's simple. Question about this? Okay, and then also we also talk about we also use Approx okay. We also used Approx TightEdge Data Structure just yesterday to get fast MaxFlow algorithm on DAGs, right? And it turns out that what I present you has some bug in it, and I will fix it now. Okay. So this is just Approx TightEdge Data Structure, and let's see. Everything is fine except here. The one that used TightEdge is just the same. But let's look at this one. Good. Okay. Right. So what's push label, right? We maintain approx like TightEdge. Like you can use Approx 1 or without Approx 1, but the key idea is that you have TightEdge. You maintain this, right? And the key idea is just try to push flow along TightEdge. Why? The intuition again is that TightEdge is at least the edge that go in the correct direction. It's go along shortest path to sync. So if you send to along TightEdge, the flow should go to sync eventually. So you just keep checking if there is some node that is not dead yet and it has some access to send, and just try to send flow along TightEdge. Push flow along TightEdge. This is TightEdge in residual graph. And if you cannot send flow, you just if there is no TightEdge, just relabel. Okay. All right. So that's the algorithm. And what was wrong? Okay. Okay, I don't get to the wrong place yet, but like what we know is like this algorithm will return a flow and label such that all the residual sink, all the sink is at level 0, and all excess is at level h, and the label will lower bound this one because every edge is delta relax. And so basically from all this, we have that we get a flow such that if you look at the node, after sending flow, look at the node with excess and the node with sink, the distance between this from here to here in terms of this weight function is at least h. Okay. But, okay, good. And I claim that like, and this is the running time, which is the running time for Approx TightEdge Data Structure. I claim in class that, and this used to be like, if you write it like multiplicative slack, this would be this one, right? This is just kind of from last class. And I claim that we can actually improve this term to be this one. I claim and said this is an exercise that you can do it, but actually I don't think it's true. Yeah.
Was it a different algorithm that the weights of the reverse edges were 0 in this?
Say again. Yeah.
There was something we did yesterday. I might just be misremembering. There was something I thought there was that it was here that we did yesterday that the reverse edge weights in the residual graph were all 0.
Right.
So.
Yeah. This is okay. So the one that use there is an algorithm that define the weight such that all forward edge have weight 1 and all backward edge has weight 0. That one don't use the push level, but without slack.
Okay.
Yeah, and that works. That works fine. Yeah. But there is the one on the DAG, and the one on the DAG, I kind of define that the weight function should be like the weight of E is tau if E is a forward edge and 0 otherwise. This is on the DAG, and I define the weight function like this. That one doesn't really work actually, and there is like it would work if we have this, because the sum of the two weight here is still big. Like the sum of the weight here is still big, but
because we're like individually summing. Like
yeah, if it's just individual here, like then it's too small. Yeah, so that's the thing that I am trying to fix now.
Okay.
Yeah, and so we don't actually have this one. Okay, and but we still have this. This is just the term from the Approx TightEdge Data Structure. This is the term for probing. This is the term for relabeling, and this is the term for updating the graph. Okay. And the term for updating the graph, we can show that it's at most this one. Like U here is just going to be at most number of saturating push, and and it can be written like this. Yeah, sum of all edge hash over backward minus slack of backward. Okay. And the way that you should think of slack is just maybe like epsilon W. So like it's still like basically it's this is like this. You should think like this is just maybe epsilon W, and this is just epsilon W here. So this is like kind of negligible. Yeah. Okay. Good. And why this is true? So like this is a term that I kind of missed in class. Yeah, but it need to be there. But it's kind of this term usually is small compared to this one. So it doesn't matter, but it need to be there. The point here is like you cannot set the slack to be, for example, bigger than W. Then like if this thing is like, if the slack here is the same as W here, then it's slow again, right? So you need to set the slack here. At least the sum of the slack should be less than the sum of the weight. That's what's important. Yeah. and here it kind of says that the slack on any edge shouldn't be too small. So for example, I cannot set the slack of forward edge to be something big and the slack of backward edge to be 0. That's not good. Okay. And but basically, like how do you bound U here? And basically, it's just about bounding the saturating push. And why this is true is kind of the same proof. And I encourage you to just go over it again. It's the same proof, but like once you kind of be careful about things being stretched, like it's this additive, like this error of the stretch, then you need to put this term here everywhere and you get this thing. Anyway, it's the same proof. So yeah. Okay. But it's just a thing that I missed. But it doesn't matter in application. But what matters is that this term, I cannot improve to this one. This is wrong. Okay, so this is the running time for push level when you use Approx TightEdge Data Structure. Okay. And so now that like you have this running time, it means that I cannot set the slack of some edge to be 0. Okay. And so the DAG algorithm like the approximate max flow on DAGs. Okay. I changed the algorithm a bit. Yeah. It has this kind of weight and slack. Okay. So instead of setting the weight on all forward edge to be something and backward edge to be 0, I just set the weight of everyone to be this, like both forward and backward. And the slack is just this much, like half of this. Okay. Okay. So why does this work? Well, like at least with this weight and slack, the running time, this term that we get will be simplified to this one, and it looks like this one. So at least the running time is good. Okay. What is the correctness? The correctness is like I just use that kind of use the same proof basically, but now I exploit that the graph is a DAG in a more essential way actually. So I don't know how much I should go over this, but like this is a part that I changed. Yeah. Like this is a part in the node that like the key thing that's the key change. So if you recall, like how do we prove this? That f is big. We basically kind of look at the graph, look at the residual graph, and imagine that we first send f1 in this graph, where f1 is like the reverse flow, and then after that we send f2, which is the maximum flow. Okay, and so we look at this sum of the flow, and we want to say that our strategy is that we analyze this sum of the flow. And if it's going to be the case, if it's the case that f here is small, then we're going to get that